A basic computer system includes a processor and a memory. They're connected by a bus, or perhaps in some cases a more sophisticated network. The bus provides the ability for the CPU and memory to talk to each other. But we also, in most systems, particularly embedded systems, have a variety of devices. Timers are very important both for the internal operation of the operating system as well as governing interactions with the outside world. We'll talk more about direct memory access, or DMA. That's a very important feature that allows more efficient transfers between different parts of the system. But many computer systems, both embedded and general purpose, have more than one bus. We use a bridge to connect one bus to another bus that may have its own devices on it, for example. We use different buses partly to separate different types of traffic. We don't want very simple devices to interfere, for example, with the transactions between the processor and the memory that need to run at high speed. But also, we may design different buses with different levels of complexity. So we may have simple buses that have cheaper, smaller, simpler interfaces for parts of the system, and more sophisticated, more expensive buses for other parts of the system. A microcontroller refers to a single chip computer system, processor, memory, and devices. The PIC16F882, which we've discussed before, is an example of a microcontroller. It has a processor, it has both flash memory and random access memory. It has its own clock and power management, and it also has a wide variety of devices, both analog and digital, connected to the bus. Many software systems are typically described as layer diagrams to show the organization of the software from lowest level closest to the hardware to the highest level applications. We refer to the hardware as a platform because it provides a complete environment in which we can design a system. The hardware abstraction layer, which is also known as a BIOS, provides the lowest level interface to the hardware and provides a level of insulation between the higher levels of software and the detailed hardware characteristics. On top of the hardware abstraction layer, we may have drivers for the different devices and also a power management system. Power management needs to understand the organization of the hardware, what can be turned on and off at different times, and how to power things down and power things up. At a higher level of abstraction, we have the operating system, whether that be a larger, more general purpose operating system or a dedicated real-time operating system. And many operating systems have file systems. On top, we have library routines, and we have the applications. We may have additional layers in between the operating system and the application, particularly in larger embedded systems. We refer to the computing system as a platform. The platform provides the hardware resources for our embedded system. The hardware abstraction layer provides a software interface to the hardware platform and hides certain details of the platform implementation from the rest of the software. Drivers for devices, of course, interact with the hardware. Power management also needs a detailed understanding of the hardware. It needs to understand how to turn different pieces of the platform on and off, and how long it takes to do that. The operating system builds on these facilities, and some operating systems have their own file system. A dedicated real-time operating system may not, however, include a file system. The application, including library routines, is built on top of this foundation. Complex embedded systems may have layers in between the operating system and the application, for instance, for middleware. The 4-cycle handshake is the basis for communication on the bus. We have two devices that want to talk to each other, and each has one line going to the other device. The inquiry or ENC signal goes from device 1 to device 2. The acknowledge or ACK signal goes back from device 2 to device 1. So, step 1, device 1 sends a signal hi. That gets the attention of device 2. When it's ready to accept the transaction, it sets its ACK signal high in step 2. When device 2 is ready, it sets its ACK signal high to tell device 1 that it can now go ahead. The data transfer occurs. Then in step 3, device 2 brings down the acknowledge signal to tell device 1 that it has successfully received the data. That causes device 1 to bring down its ENC signal, and now both signals at their original low state. So we can perform another 4-cycle handshake in order to transfer another piece of data. The handshake means that we don't have to have explicit fixed timing for the transfer. If one side needs to take a little longer, it can do so by proper signaling of the ENC and the ACK. A bus system for a processor looks something like this. The details may vary, but this gives you an idea of the main components of a bus. Most buses today are clocked. They're explicitly synchronized. The clock for the bus is usually at a slower rate than the internal processor clock. A read-write signal tells whether a transaction is reading or writing. Address lines give the address for the transaction. Data lines give data, and we have a data ready signal. In some cases, we may share the data and address lines. This, of course, requires the bus protocol to operate more slowly, since we cannot send data and address simultaneously. We use timing diagrams to describe buses and other types of logic. A stable signal is drawn as a pair of lines, low and high. We don't know whether the particular signal is low or high in this case. That depends upon the situation and the particular data. But we know that whatever value it has, that value is a stable, valid logic value. A changing signal that is not stable is represented by a line through the middle. And of course, we can use timing constraints to show the relative operation of events. In this case, signal B happens before signal C. This timing constraint does not have an explicit time on it. All it says is that B has to go stable before C goes stable. But some timing constraints may have times labeled on them saying how long is the interval from the first event to the second event. So we can use timing diagrams to describe read and write operations on buses. The read-write signal in this case is high, signifying a read. An address enable line is used to signal that the values on the address lines are in fact valid. After a certain amount of time, a data ready signal, which is in this case negative logic, goes low to indicate that the data is in fact ready. A write transformation is similar. In this case, though, the read-write signal is low to indicate a write. We can describe the two sides of a bus transaction as state machines, one for the processor and the other for the device. So we have a start state on each side that generally, so we have a start state on each side in which the CPU is going to send an address and the device expects an address. The bus operation cycle starts with an address phase in which the CPU sends an address and the device expects to see an address. Each side waits to perform some processing. When the device is ready, it sends an acknowledgement. The CPU then sees an acknowledgement and it gets the data to be ready and sends it to the device, which receives the data. When the device is ready, it sends an acknowledgement, which causes the CPU to recognize the operation is done, and then it ends up in its address space. Similarly, the device ends up in its own address state. Buses that use clocks need to wait a certain number. Bus transactions can take varying amounts of time. Some devices, some types of memory, may be slower than others. When a bus is clocked, we need to insert wait states as part of the transaction. So in this case, the memory is not ready to perform the operation for an extra cycle. That cycle is known as a wait state. An important way to make buses more efficient is with burst transactions. We have a separate signal that signals that we have a burst transaction for several values and not just a single value. Burst transactions can be performed with varying amounts of information, but the basic idea is you access a sequence of locations, not just a single location. So in this case, the burst transaction starts with the starting address for the burst, and then the address is incremented implicitly during the memory access. So we get 1, 2, 3, 4 data accesses for one address transfer on the bus. We've therefore saved quite a bit amount of time. How do we build a bus? Well, each device needs to have some logic to determine when it's being talked to, right? So the address enable line on the processor is used to clock a register in the device. If the address matches the address of the device, it then takes advantage of the data enable signal to tell when the data is actually on the bus. The address enable line can be used to control a register that loads the address from the bus into the processor. The device can then look at that address and decide if it is the target of this transfer. If so, the data enable line tells the device when to either look for the data that's being written or to provide the data that's being read. Once again, here's our generic computing system. Direct memory access, or DMA, is an important mechanism that we see in both small and large systems. Direct memory access is a specialized device that performs transfers on the bus without executing a program. DMA access is more efficient, faster than programmed transfers on the bus. DMA uses two signals in a 4-cycle handshake. It uses a bus request signal to ask the CPU for bus mastership. In most cases, the CPU acts as the master of the bus. It controls the bus operation, sets the bus control signals, and determines when things happen. If DMA is to perform independent transfers, it needs to be able to become bus master. So it uses two signals in a 4-cycle handshake to request bus mastership. The CPU typically operates as the bus master. That is, it controls when things happen on the bus, and it controls the value of the control signals on the bus. If the DMA is going to perform an independent memory transfer, it needs to be able to request bus mastership, and it uses a pair of signals and a 4-cycle handshake in order to request that mastership. The bus request signal is used to let the DMA. The bus request signal allows the DMA engine to request bus mastership. When the CPU is ready to grant bus mastership, it uses the bus grant signal. If, for example, the CPU is executing instruction, it may not be immediately ready to grant the bus request. It may want to empty out certain instructions from the pipeline, finish certain memory operations, and so forth. So the bus request and bus grant signals act as INC and ACT signals for the particular bus mastership protocol. The CPU and the DMA engine, of course, share the bus. In general, since the CPU can't use the bus at the same time as the DMA unit, DMA often breaks up very large transfers into small chunks. So, for example, the CPU is executing, a timer in the DMA goes off and says, I want to grab the bus and perform a transfer. When it receives bus mastership, it then performs a certain number of transfers and then returns control back to the CPU. After a certain amount of time, the timer in the DMA goes off again and asks for bus mastership, performs another operation, then returns to the CPU, and the cycle continues until the complete transfer is finished. The CPU has to stall in general while the DMA is using the bus. If it has values in its cache, or in its registers, it may be able to execute for a certain amount of time. But once it needs the bus, it has to wait for a DMA operation to finish. And that's why it's so important that a DMA unit be able to break a large transfer into small chunks. As we saw before, we can build multiple buses of different types in a system and use bridges to connect the different types of buses. We may want to have a slow, simple bus and a fast, high-performance bus. We may want to segregate. We can use these for both cost reasons and to help segregate traffic between slow and fast devices. As we saw before, we have high-speed and low-speed devices. We may want to have separate devices. As we saw before, we may have several buses in a system. We may want one bus for high-speed devices. We may want a separate bus for slower devices. This both reduces the cost of the system and helps segregate traffic. The bridge is basically a protocol engine. It understands the protocol of one bus on one side, and it also understands the protocol of the other bus on the other side. And it has a state machine that will translate between the slow and fast protocols. It also, in general, needs registers to temporarily store values during a transfer. ARM has developed several different buses. The AMBA High Performance Bus, or AHB, is designed for CPU memory operations. The AMBA Peripherals Bus, or APB, is a simpler, lower-cost bus designed for low-speed I/O devices. Memory components can come in different capacities, different sizes, as well as different widths. We can have a memory that has a small number of bits on its input-output pins, or a wider number of bits. We can also have different memory technologies: dynamic RAM or DRAM, static RAM or SRAM, and flash. All of these technologies, though, share a same basic organization. A memory is a two-dimensional structure, and we use an address to access locations in that memory. So the address comes in as n bits. We can divide the address into two pieces: the row address and the column address. We use the row address to select a horizontal row in the memory array, and then we use the column address to select one or perhaps several vertical columns in the array. We can use this same structure for both reading and writing. Dynamic RAM, or DRAM, is a smaller circuit than is SRAM. However, the values in dynamic RAM can disappear over time. So we need to refresh those values in order to ensure that the values stored in the DRAM are valid. Static RAM is often used in caches. It's the basis of register circuits. It's faster, but it's also less dense than DRAM, and it consumes more power. We have several types of memory technology: extended data out DRAM, fast page mode DRAM, double data rate DRAM, and various versions of DDR. The term SIM stands for Single Inline Memory Module, which is a particular package for a set of memory chips. A DIMM is a double inline memory module. memory cost is very important. So memory has developed a particular strategy to the cost of a memory chip is very important. They're sold in huge quantities. So memory chips have developed a particular strategy to reduce the number of pins, which is to break the address into two pieces known as the row and the column. So the two control signals that describe the timing in a classic DRAM are called RAS for row address select and CAS for column address select. So the address lines are used first for the row address and then for the column address. Early memories had no clock, so the RAS and CAS signals were used directly for timing. Modern high-performance DRAMs have a clock, but we still maintain this RAS-CAS terminology to describe the different parts of the address operation. We usually don't connect memory directly to the CPU. We use a memory controller to interface between the CPU and the memory. The memory controller has two purposes. First, it insulates the CPU for certain details of the memory operation. Modern memory chips have all sorts of timing parameters that need to be programmed into the interface to the memory. Memory controllers can automatically detect the speed of the installed memory and set registers appropriately. Memories also provide parallelism, and the memory controller provides registers and simple algorithms to take advantage of that memory parallelism. They may in fact reorder certain memory operations in order to improve memory system performance. Many memory systems consist of not one memory array but multiple memory arrays. So we can organize a given block of memory into banks. Each bank is a two-dimensional array that provides one form of parallelism. But we can also have multiple banks spread across different channels. The CPU provides multiple channels that can operate in parallel, and this provides a separate form of parallels in the memory system. Taking advantage of that parallelism is an important part of software design for embedded computing systems.